At the very front of logical headway is the European Gathering for Atomic Examination, CERN, prestigious for its notable commitments to molecule material science. As of late, the amazingly popular Molecule Material Science Research Facility has uncovered an incredibly uncommon finding from its enormous Hadron Collider that could totally change how we might interpret the universe. Researchers accept these abnormal discoveries could uncover the presence of outsider life in an equal reality. This historic thought has ignited fervor and extreme conversation among specialists. Could this striking disclosure reshape how we might interpret the universe? Furthermore, whenever affirmed, what significant experiences will this disclosure offer into the nature of reality itself? Go along with us as we dig into the as-of-late distributed discoveries, investigating how CERN researchers are ending their quietness on this chilling new disclosure that has the potential to change all that we know. The European Gathering for Atomic Research, also called CERN, has been popular for its thrill-seeking tests since its commencement during the 1950s. It has been at the center of attention a few times for good, however. Its tests have stimulated worry about the potential arrangement of dark openings, breaks in our reality, and numerous different dangers. One of CERN's most popular and dubious accomplishments was the development of the Huge Hadron Collider, LHC. The LHC is the world's biggest atom smasher, starting operation on September 10, 2008, and remains the latest expansion to CERN's gas pedal complex. Crossing more than 27 kilometers of superconducting magnets and a progression of speeding up gadgets, the CERN super-innovation cost more than $4.5 billion. Many would contend that this cash was astutely spent since the LHC has brought about probably the most significant revelations of the last many years. For example, the discovery of the Higgs boson and numerous other beforehand obscure particles. This gigantic machine is fit for speeding various particles around the circle until they reach close to light speed and complete more than 11,000 laps. The LHC does this with a series of extremely strong electromagnets that produce a magnetic field inside the accelerator that is nearly 100,000 times more prominent than the field that encompasses the Earth. Some have communicated worry about the effect of making such strong fields on nearby hardware, as well as its impact on the Earth's own field. Once these particles reach their most extreme speed, multiple times the speed of light, particles heading down conflicting paths are compelled to meet in a vicious impact, delivering tremendous energy and a variety of particles. When particles impact, a flood of particles escapes out this way and that, with most of them enduring just parts of a second before fading. Changing the source of particles permits analysts to reveal new particles. In this whirlwind, exceptionally created ultrasensitive finders are introduced around the impact destinations to record all the data from each crash. This measure of information mounts up rapidly and needs a huge amount of time and work to go through consistently. The LHC's analyses create more than 15 petabytes of crude information from these crashes, which need to be deliberately figured out to extricate the information the analysts need. In 2017, the LHC accomplished a critical achievement by forever putting away more than 200 petabytes of information in its tape libraries. To place this amount of information in perspective, 1 petabyte is equivalent to around 250,000 films. However, what precisely are they searching for in all of this information? They identified something going on with a particular kind of particles, quarks, the major building blocks of matter, and exist in various flavors as characterized by physicists. A portion of these quark flavors are truly unstable, decaying into different particles in the blink of an eye. The beauty quark, with a normal life expectancy of 1.2 trillionth of a second, turned into the focal point of consideration due to a particular distortion. Its decay pattern contrasted from what researchers anticipated in light of the Standard Model. As indicated by their expectations, when a beauty quark decays, it will be affected by the weak force and transform into a bunch of lighter particles known as leptons, either an electron or a muon, with the Standard Model foreseeing a 50/50th chance for the two particles. However, the LHC information uncovered that these quarks decayed into muons only 70% of the time, as opposed to decaying into electrons. This uniqueness could exist if a previously obscure kind of particle is engaged in the process. This has driven a few scholars to think that some new type of physical science might be working. A new force-carrying particle would infer shiny new physical science that could expand the Standard Model and answer many befuddling questions. The chance of new material science challenges the Standard Model hypothesis, which provides our best understanding of how the odd universe of particles acts. The Standard Model is a logical structure that unequivocally makes sense of each and every part of our insight into the actual world's building components. The shocking thing is that, regardless of this serious level of exactness, physicists are very much aware that this model still needs to be completed. The Standard Model only describes three central forces: electromagnetic force, strong force, and weak force. There is currently no description of gravity force or a clarification for dark matter, the universe's predominant sort of issue. During ongoing preliminaries, scientists found a disparity in the information they were assessing that contrasted from why the Standard Model predicts. Although it isn't unusual to find results beyond this framework given the volume of information delivered by the LHC, this time something piqued researchers' interest, and they saw the need to explore more to decide this new phenomenon. What might this shiny new force eventually be? To make sense of this surprising disclosure, the scientists hypothesized the presence of another fundamental particle, which they allude to as Z', a force-carrying particle. Despite the fact that this force is the best bet, it is incredibly weak because there have been no indications of it up to this point. The specialists believe it would interact in an unexpected way with electrons and muons. However, the degree of its interactions with Standard Model particles remains obscure for the time being. If researchers found new force-carrying particles, it would be a decade's hotly anticipated breakthrough in material science. Physicists trust that if this revelation is confirmed, it will serve to disentangle well-established secrets of the universe and make sense of age-old problems such as what dark matter is and the Higgs boson's role in the current day. Some researchers believe that this unseen force could help fulfill one of physics' most significant objectives over the last century, bringing together the fundamental forces of existence. As per Elon Musk, CERN fabricated the largest and most noteworthy energy molecule collider in human history, the Large Hadron Collider, between 1998 and 2008. More than 10,000 researchers, many institutions and labs from over 100 countries assisted with this process. It sits inside a 27 kilometers long tunnel on the border between France and Switzerland, close to Geneva, around 175 meters underground. The very first impact recorded at the Large Hadron Collider had an energy of 3.5 tera-electron-volts per beam, roughly multiple times that of the previous world record. The energy came to 6.5 tera-electron-volts per beam once the LHC was additionally improved. Musk noted that the Large Hadron Collider excels at proton beam collisions. Besides, it can accelerate lead-ion beams specifically. Consistently, proton and lead impacts are regularly conducted for 1 month for researchers testing the expectations of several molecule material science hypotheses. The primary objective of the Large Hadron Collider is to test the properties of the Higgs boson and look for the large group of new particles anticipated by subatomic molecule speculations. Hadrons are composite subatomic particles comprised of quarks that are held intact by a strong force, much as how atoms and molecules are held together by the electromagnetic force. Protons and neutrons are two examples of hadrons that are generally recognized, including the pions and kaons, which were discovered for the first time in cosmic ray tests in the late 1940s and mid-1950s. The LHC brings two colliding particle beams together so they can impact. The Higgs boson is remembered to be a fundamental particle associated with the Higgs field. It is the quantum excitation of this field. Like how you notice waves in the ocean, the boson resembles a pristine species in the particle zoo. It lacks the quantum attributes of fundamental matter, as well as the carriers of quantum interactions like electromagnetic force, weak force, and strong interactions. The Higgs boson was discovered at the Large Hadron Collider, a pivotal finding accomplished simultaneously by the two significant multifunctional experiments, ATLAS and CMS. It was announced on July 4, 2012 at CERN. At the time, the new scalar boson was found primarily in two rare decay channels that gave the most perfect signal: decay into a couple of photons, which required an absolutely quantum virtual process, and direct decay into a couple of Z bosons, the carrier of the neutral-weak interaction. Although the discovery of the Higgs boson at the time established the Standard Model, examination into this elusive particle didn't end there. One of the main discoveries since 2012 was the confirmation of Higgs decay. As indicated by CERN, at the time, the investigation into this tricky particle would evolve during the LHC's third cycle, particularly once the particle accelerator's high luminosity upgrade is completed in 2029. This will permit the LHC to undertake more collisions, giving analysts more opportunities to identify strange physical science, for example, events that don't fit into the standard model. CERN estimates that when the accelerator is upgraded every year, it will produce 15 million of these particles. This compares to the LHC's production of 3 million Higgs bosons in 2017. This may be helpful for recognizing different kinds of Higgs boson speculations that go beyond the standard. The recent discovery at CERN is profoundly intriguing because it points to the possibility of new physics beyond the standard model. Researchers have noted unusual behavior in particles that could indicate the presence of new forces or particles. This discovery raises the exciting possibility of uncovering new dimensions or previously unknown aspects of reality. The Large Hadron Collider's experiments have consistently pushed the boundaries of our understanding, from confirming the Higgs boson to exploring anomalies that challenge existing theories. The latest data suggest that we might be on the brink of discovering phenomena that could revolutionize our comprehension of the universe. For instance, if the presence of a new particle like Z' is confirmed, it could explain inconsistencies in our current models and provide new insights into fundamental questions about the nature of matter and forces. These discoveries also have broader implications for our understanding of the universe. The possibility of new fundamental particles or forces could help address long-standing questions such as the nature of dark matter and the integration of gravity into quantum mechanics. It might also offer new perspectives on the origin of the universe and the forces that govern its behavior. As CERN continues its groundbreaking work, the scientific community remains hopeful that these new findings will lead to significant advancements in particle physics. The ongoing research and experiments at the LHC are essential for uncovering the mysteries of the universe and expanding our knowledge of the physical world. The excitement and anticipation surrounding these discoveries underscore the importance of continued exploration and innovation in science. In conclusion, the recent developments at CERN are more than just a technical achievement. They represent a potential paradigm shift in our understanding of the universe. As scientists delve deeper into these findings, they may unlock new realms of knowledge that could reshape our view of reality. The journey to unravel these mysteries is just beginning, and the future holds promising possibilities for discovery and advancement in the field of particle physics.